Hello, everyone. I'm here to discuss Team Five's project for ECE 4960 Senior Design 2. The project that me and my teammates have come up with is the EZ-Caddy, which is an autonomous golf push cart. Our charter for the our project was to develop a motor that will be installed onto a manual push cart and that will allow the user to control the direction, speed, and have detection for where the user will be with machine vision on the golf course. This project had a set deadline to be completed by November 19th, 2025, and our budget was $700. My name is Stephen Massey, and you will hear from Austin Hill, Connor Bohannon, and Trevor Lynch throughout the course of this presentation. When it comes to the motivation behind this project, one of our main goals was to just overall uh, complete convenience for this golf push cart. We wanted to make it user-friendly to anybody that could use it while also having a good budget for the project. So when it comes to our key points, one of the main ones was to reduce the physical labor for golfers. This could come from creating an alternate solution for people that may have a preference for carrying their bag or actually using a golf push cart. There's many push carts that are in the market that require a constant manual effort to push that golf bag uphill or on soft terrain. This golf bag, these typical push carts can can be a little tiring for a lot of users while you're having to walk and drag a bag along for 18 holes. That could lead to fatigue, lower back tension, shoulder soreness from lugging that bag around. And those are just a few examples of what could happen when you use a manual push cart. Another motivational factor was to basically have the user not even have to worry about where their bag is and just have a sense that they know that their bag is following them throughout the course. We also wanted to aim to increase the accessibility of this product for seniors, youth, limited mobility players, and other players. We wanted to just make an overall better experience when it comes to walking at the golf course in the time where riding in a golf cart is the most convenient factor for people. Not only does walking in a golf rounds usually cheaper, but it gives you that beneficial exercising factor that you get within golf. We also wanted to make sure that we had an eco-friendly alternative with the minimal turf impact that the push cart would actually have, where golf carts can typically leave a bunch of damage that are on the grass whenever they tend to drive them out. We wanted to make sure that we could basically eliminate that factor. And finally, we just wanted to make sure that our product was cost effective compared to the current market of automated push carts.
My name is Connor Bohannon. I was one of the software leads on this project, and today I'll be talking about our problem definition. So for this project, our team set out to build the EZ-Caddy, which is a powered push cart that is capable of both autonomous following and the manual control. So our deliverables focused on four major areas. First, we needed a fully monitored cart that could track and follow a user using computer vision at speeds up to 5 miles per hour while supporting at least a 30-pound load. Secondly, we built a Bluetooth connected website that allows manual driving, emergency stopping, and battery monitoring. Thirdly, we documented the entire system and demonstrated a 30 to 60 minutes of continuous autonomous operation. And finally, we performed safety compliance testing, ensuring that emergency stop was reliable and the cart halted safely within a half a meter of obstacles. These deliverables guided the engineering decisions you'll see next. So moving on to our system block diagram. This block diagram shows the complete system architecture for the EZ-Caddy. At the center is our Raspberry Pi, which acts as the control unit and processes all sensor data and user command. The Pi receives video from the camera for tracking motion data, and the manual control inputs through Bluetooth from the phone interface. Based on those inputs, the Pi generates PWM and direction signals that drive the left and right motors through two H-bridge motor drives. The entire system is powered by a battery and regulated through a voltage regulator to ensure stable voltage to the Pi and motor electronics. Structurally, the design is modular, so we can debug or upgrade subsystems independently. Moving on to our hardware components. These images on the left show the major hardware components that make up our system. We used high torque DC motors capable of moving over 30 pounds with consistent speed control. The H-brake drivers allow forward and reverse operations as well as precise PWM speed control. Our onboard camera provides the frames needed for target tracking, while the accelerometer and gyro stabilize our motion control and help smooth out noisy inputs. The voltage regulator and battery assembly provide clean and reliable power to both the control electronics and motors. The remaining image show our wiring, connectors, and mounting solutions that kept the system organized and serviceable. Next, I'd like to move on and talk about the flowchart. This flowchart here illustrates the full control logic of the EZ-Caddy. When the system starts, the Raspberry Pi initializes all sensors, the BLE controller, the camera, and the background threads that monitor both joystick and auto follow inputs. From there, the system constantly evaluates whether the user is manually controlling the cart or if the autonomous mode should take over. A continuous safety thread monitors for humans or obstacles entering a restricted zone, and if anything is detected, the emergency stop routine immediately shuts down the motors. In manual mode, joysticks input drive the motors directly, while in autofollow mode, the camera determines the target's position and distance and computes the motor commands accordingly. All pathways ultimately feed into the motor control block that sets wheel speeds and the directions. Next, we'll talk about the website interface. So this is our custom web-based control interface for the EZ-Caddy. The site connects to the Raspberry Pi over BLE, or Bluetooth Low Energy, allowing a user to manually drive the cart from their phone or laptop. The joystick widget on the left sends X and Y values in the real time, and the interface includes a clear emergency stop button that overrides all commands instantly. We also display battery percentage and include a map for situational awareness during testing. The interface is simple, responsive, and it gives the user full control when autonomous mode is not desired. Finally, I will be discussing our design. Here you can see our final prototype and internal wiring layout. We mounted the electronics centrally on the frame to improve stability and protect components during movement. One challenge we faced was electrical noise from the motors interfering with the Pi and camera. So we isolated grounds and improved cable routing to reduce interference. Another challenge was ensuring reliable Bluetooth performance outdoors, which we solved by repositioning the antenna and optimizing our update rate. Overall, the final system meets our deliverable requirements, supports both manual and autonomous operations, and perform reliability under real-world load and terrain. Thank you, and that is all for my part.
I'm Trevor Lynch, and I'll be talking about the challenges and strengths we had with our senior design project. So, one of the major challenges was the 3D printed mounts that made it a little bit hard to get perfect control on the wheels of the push cart. They would sometimes slip because with the extra weight of the golf bag, these the wheels would bend out, giving less contact for the 3D printed gears. This could be improved by having two supports for the gears rather than just on the motor side, and also having stiffer mounts. We also had some trouble with Bluetooth Low Energy connectivity and web browser integration. Getting that working, now that we have it working, it is pretty seamless to where you just open your web browser to the right IP and connect. Person detection was kind of hard to get working with the model, and right now we have it to where it detects feet and legs and then tracks those. That could be improved. Um, Getting distance with the camera was also hard because there's no real good way to measure the size of something or how close it is. So what we ended up doing was it measures how big of a box is created around your feet and legs to actually maneuver the cart and tell how far it is away from you and stop in time. Also, autonomous mode struggled a little uphill because we didn't have the motors turned up all the way. We could turn motors up that would actually let it keep up with us. Some of the strengths were person detection. It's completely functional and it will follow someone perfectly from farther away. It keeps a constant speed no matter how far you are away or how you're controlling it, which is very good. Um, Manual mode with the joystick on the app works really well and is very precise. GPS, you can see exactly where you and the push cart are on the app, which is helpful. Um, we have a constant speed downhill, so the motors don't get overwhelmed and just let the push cart go. And the push cart also will always stop and won't move unless the person steps away from the push cart, so it won't run someone over. And it also won't run into objects unless someone walks right by that object.
My name is Austin Hill, and I will be commenting over our demonstration video. Here you can see our website application turning on our autonomous following mode. You'll see the EZ-Caddy following or keeping our golfer in its center line. And throughout this video, you will see it traveling across various terrains. As we were testing our EZ-Caddy, we tested it for over an hour, helping us reach our first deliverable. Here you can see our emergency stop, as well as our automatic start as the golfer walks in and out of range. Here you can see our website application in its manual drive mode, which you can use the joystick to control the speed and direction of the EZ-Caddy, as well as start and stop functionality. Here's another demonstration of our EZ-Caddy on different terrains. Here you can see it traveling uphill on a cart path. Here's another demonstration of the emergency stop and automatic start. As the EZ-Caddy comes within range of our golfer, it will automatically stop. And as they leave that range, it'll start up again. Here you can also see another demonstration of the autonomous following. As our golfer walks from right, left, and left to right, you can see the golf caddy keeping him in its center line